Alright, in this video I'm going to draw your attention to some facts about polynomials in terms of their end behavior and how the end behavior relates to the polynomial itself. So here I have a definition of a polynomial, which it looks kind of crazy, but we do need definitions for things like this, right? If I ask you what a polynomial is, you might be able to describe it briefly, generally, but this here is the true definition of what a polynomial is. So don't get confused by the notation. All we're saying is that a polynomial of degree n can be written in this form. So you've got a number, a sub n times x to the n. So that's the degree of the polynomial because that's the highest power in this whole polynomial here. That's why it says here a sub n cannot be 0. Because if a sub n was 0, then this term would be 0, and then the highest power would be x to the n minus 1. But then it wouldn't be a degree n polynomial. So that's all this is saying. The other thing is when the degrees are written in descending order, so look, this is x to the n minus 1, n minus 2, etc., squared to the 1, and then x to the 0. It's called written in standard form. And when it's in standard form, it's easy to see the degree. Okay, so this is just kind of a review of those things. But like if I give you just, I give you this polynomial here, 4x cubed plus 5x squared minus x plus 10. Well, this here is called my leading term. It's the leading term because it's the not because it's just the first term written, because I could have written like the 5x squared first, and the negative x second, and then this third, and the net to 10 last. But when you write it in standard form, so see how the degrees are going down, then this is called the leading term. And the 4 there is like your up here. This is your a sub n. In this case, n is 3, so that's like my a sub 3. This 10 would be my a sub 0. And the 4 is the leading coefficient. So the a sub 3 is called the leading coefficient. So if I use those terms, you should know what those mean. Okay, so now let's just take a look at this chart I have here. What I've done is I've sort of divided up all the cases you can have when you're looking at a polynomial, right? The degree of a polynomial can either be even, which is this column, or the degree of a polynomial can be odd, which is this column. Your leading term could be positive, so for instance, that's a positive 4, and that's a positive 2, or your leading term could be negative. That's a negative 4, and that's a negative 3. Actually, I kind of made a mistake here. We have to examine this a little bit more closely. This is not written in standard form, and I did that on purpose. Let's write it in standard form. We got to put the highest degree first, so that's a 3x cubed. So before I call this a degree 2, we got to make sure we get things in order so we don't make a mistake. This is degree 3, right? Once you rearrange things, so be aware of those kind of tricks that we teachers throw in to mess you up. So that's actually degree 3. So it's an odd degree, so it belongs in that column. So what we're going to do is kind of look at the end behaviors of these polynomials. So let's look at this one here. This is 4x to the 4th, so the degree is even. The leading term is positive. So what does that mean about the end behavior of this graph, or just the graph in general? How does it look? Well, in terms of the end behavior, that means what's happening to this function as we plug in x values that are approaching infinity and negative infinity. So think about like plugging in 1,000,000. 4 times 1,000,000 to the 4th, that's a really big positive number, right? 4 times 1,000,000 to the 4th is a really big positive number. Plus 2 times 1,000,000 minus 1. Well, adding that 2 times 1,000,000 minus 1 is really, it's going to increase the number. But really what's contributing most to the number itself is this here, especially for x values that are really big. So when x is really large, what's contributing most to the output is this here. So we can do all our analysis on the leading term. So again, as x goes to infinity, this becomes really big, a really big positive number. So that means our graph's probably doing that in the long run. Right. Now, on the other hand, if I plug in a number like negative a million, then I've got 4 times negative a million to the fourth. 4 times negative a million to the fourth. Okay, so we just do our analysis on that. Well, what kind of number is negative a million to the fourth? It's a really big positive number because you're multiplying a negative times itself 4 times. So this becomes a positive number times a positive, so that's also positive. So when you plug in a really big negative x value, it also goes to infinity. So that's why the shape of your polynomial that has an even degree, whose leading coefficient is positive, tends to look like this. And so now we know the answers to these questions. All right. On the other hand, let's do our analysis here. If I plug in that, if I go towards infinity, as x goes to infinity, and again, I can just do my analysis on this because this contributes most to the number. These guys over here don't really, they're kind of like drops in the bucket in the long run in terms of the outputs of the function. Plug in like a million. 3 times a million cubed is a really big positive number. So that means that this function in the long run is going to go off to positive infinity. On the other hand, if you plug in a number like negative a million, then 3 times negative a million cubed, well, 3 times negative a million cubed, that's a positive number times a really big negative number because this is a negative times a negative times a negative. So this becomes a really big negative number, which means as x goes to negative infinity, the y values go to negative infinity. So that's why odd degree polynomials tend to have that overall end behavior shape. And so that's what justifies these answers here. On the other hand, if I've got a degree 4, or an even degree, and I'm considering the end behavior, so let's think about like really big positive x values. And again, we can do all our analysis just on that term. Well, this is like negative number, negative 4 times a million cubed. I mean, a million to the fourth. A million to the fourth is a really big positive number. But that, when you multiply that times a negative 4, it makes it a really big negative number. So in the long run, the graph tends towards negative infinity. On the other hand, if you plug in negative 4 times, negative a million to the fourth, this is a really big positive number times a negative, makes it a really big negative number. Okay, so even degree functions, and I'm sure you've noticed this in class, they tend to have end behaviors that are the same. So that justifies these answers. And lastly, if we have an odd degree function, we can do our analysis just on this term. You plug in a big positive number, like a million cubed, you get a million cubed, that's positive, times a negative 3. It's a big negative number. On the other hand, if you plug in like negative a million, then you get negative 3 times negative a million cubed. That's a negative number. This is a really big negative number because it's a negative times a negative times a negative. So it's a negative times a negative, which is positive. So it's a really big positive number. So as x goes to infinity, the y values are going towards positive infinity. And so odd degrees functions whose leading coefficient is negative tend to look like this. And that justifies these answers. So again, the thing to notice, first of all, notice the reasoning I use to justify these answers. A lot of students try to sort of remember the rules, like, oh, if it's even degree and the leading coefficient is positive, then it sort of looks like this, the end behaviors are the same and they're going up. That's fine if you want to memorize all these rules, but just note that they all came from this idea that you can just look at the leading term and do your analysis on that, and then just imagine what happens when you plug in big positive and big negative numbers, and all this sort of falls into place. All right. Again, the one thing I kind of fudged is like we don't know much about the details in the middle, so even though like my sketch looks like, it looks like this is a cubic and this is probably a degree 4, we don't really know the details. This slide is really meant to draw your attention to the end behaviors. So I kind of just like threw up, put in some random sketch in between, but it's the end behaviors you want to focus on. And you can get all that information from the polynomial itself without having to graph it.